Spill a glass of water and it doesn't stay in a neat pile. It spreads. It finds every crevice, every dip, relentlessly seeking out the lowest point. This seemingly simple act is actually a profound demonstration of one of physics' most fundamental principles, hydrostatic pressure. It's a force so ubiquitous, so ingrained in our world, that we barely notice its incredible power, yet it shapes everything from our plumbing to the very landscape of our planet. We often take water's behavior for granted, seeing it merely as a liquid that flows. But its tendency to seek its own level isn't just about gravity pulling it downwards. It's about how water and all fluids distribute pressure evenly within themselves, a silent, constant negotiation between countless tiny molecules. To truly appreciate this, let's start with a single drop. Imagine it suspended, then released. Gravity pulls it down. But what happens when that single drop joins a billion others in a glass, or a lake, or even an ocean? How do they all decide where to go? The answer lies in understanding pressure, specifically the pressure exerted by a fluid at rest. This is what hydrostatic means, hydro for water and static for still. It's the weight of the water above a certain point, pushing down, but critically, that pressure isn't just directed downwards. Unlike a solid which holds its shape and transmits force in a specific direction, a liquid transmits pressure equally in all directions. Think of it like a perfectly spherical balloon filled with water. If you squeeze one side, the balloon bulges out everywhere else. That's pressure being distributed. So when we talk about water seeking its own level, we're really talking about a state of equilibrium. Water will flow until the pressure at any given horizontal level within the connected body of water is equal. If there's a higher point, the water there has more weight above it, creating greater pressure. This higher pressure then pushes water towards areas of lower pressure, which are usually lower elevations. It's a continuous dance, a constant adjustment, until every single water molecule is as comfortable as it can be, with no net force pushing it in any particular direction. Consider a simple U-tube. If you pour water into one side, it rises in the other until both levels match. This isn't magic, it's hydrostatic pressure at work. The weight of the water in the higher column creates more pressure at the bottom of that column, pushing water up the other side until the pressures equalize. This principle, sometimes called Pascal's law for fluids at rest, was articulated by the French mathematician and physicist Blaise Pascal in the 17th century. He built upon earlier work, but his formulations helped cement our understanding of how fluids behave, laying groundwork for much of modern hydraulics. Pascal's experiments weren't just theoretical. They had practical implications. Think about how a hydraulic jack lifts a car. A small force applied over a small area creates a large pressure, which is then transmitted throughout the fluid to a larger area, generating a much larger force. It's all connected to this idea of pressure distribution. But the power of hydrostatic pressure isn't just for heavy machinery. It's quietly at play in the very infrastructure of our cities. Water towers, for instance, don't use pumps to deliver water to your home. Not directly, anyway. They rely almost entirely on gravity and hydrostatic pressure. By placing a massive reservoir of water high above the ground, the water tower creates a significant column of water. This column exerts pressure, forcing water through pipes into your home and out of your tap. The higher the tower, the greater the pressure and the stronger the flow. It's an incredibly energy-efficient system once the water is pumped up to the tower. From there, it's pure physics. No constant pumping needed, just the quiet, persistent force of water pushing itself down and out, seeking its level relative to everything else connected to the system. This also explains why your shower pressure might be lower on the second floor than on the first. The water on the first floor has a taller column of water above it from the water tower, thus more hydrostatic pressure pushing it out. On the second floor, that column is slightly shorter. And it's not just about water we control. Think about natural springs or artesian wells. These occur when groundwater, trapped under pressure by impermeable rock layers, finds a path to the surface. The pressure from the higher elevation of the water source forces it upwards, sometimes in a powerful jet. Even the intricate network of rivers and lakes across our planet is a grand display of hydrostatic principles. Water always flows from higher elevations to lower ones, carving out valleys and shaping landscapes, relentlessly making its way towards the ultimate low point, the ocean. And within the ocean itself, hydrostatic pressure creates incredible forces. For every 10 meters you descend in the ocean, the pressure increases by roughly 1 atmosphere. That's about 14.7 pounds per square inch. At the bottom of the Mariana Trench, the deepest part of the ocean, the pressure is over 1,000 times that at sea level. This immense pressure crushes anything not specifically designed to withstand it, yet life thrives in these extreme environments, adapted to the constant, powerful squeeze. So the next time you see a still pond, or watch water drain from a bathtub, pause for a moment. You're witnessing the silent, ceaseless work of hydrostatic pressure. It's not just water finding its level. It's a profound declaration of equilibrium, a demonstration of forces balancing out. It's a principle that guides engineers, shapes our natural world, and quietly powers much of our daily lives. From the coffee brewing in your kitchen to the vast oceans, this simple tendency of water is a testament to the elegant, powerful rules that govern our physical reality. It's a reminder that even the most ordinary phenomena often hold the deepest scientific truths, waiting for us to look a little closer, to ask why. And when we do, the world reveals its incredible, intricate design. What other obvious phenomena hold surprising scientific secrets? Let me know in the comments, and you just might see it in our next exploration.